Day 68, page 272, rotational kinematics, problem 35. Here's kind of a fun one because I don't think we've done this before. But we all know that when you're going in a circle, there's a centripetal acceleration towards the center. And usually we're dealing with circular motion that's uniform. In other words, not speeding up rotationally like this problem is. So there's two components to the acceleration in this case. We have our typical centripetal acceleration at that particular instant based on, well, down here, centripetal acceleration is your tangential velocity squared over r, v squared over r. That's the equation that we have for centripetal acceleration if we know our instantaneous velocity at that time. And that's tangential. But I haven't drawn the velocity vector here. This is the tangential acceleration that's related to the rotational acceleration of 4 radians per second squared. And the relationship between tangential acceleration is r times your alpha. In this case, we know alpha is 4, so I switch this around. So I'm bringing that down here. So that's my alpha given in the problem, 4 radians per second squared times r. So that's my tangential component of the overall acceleration. And then, like I said, this is the generic equation for centripetal acceleration. And then the relationship between tangential velocity and your rotational velocity. That's all given. All right? Now here's the vector diagram. Luckily, fortunately, the centripetal acceleration towards the center of the circle is perpendicular to the tangential acceleration. And they give us the overall acceleration of 8 meters per second squared, which is just be the Pythagorean triple for a sub c, a sub t, and then our hypotenuse. So basic application of Pythagorean theorem, a sub c squared plus a sub t squared equals 8 squared. And now it's just all algebra plugging everything in. It gets kind of fun here, if you like this kind of stuff. So I'm going to move this up a little bit and see if this works. Sorry about that. But bottom line is, okay, so I plug in for centripetal acceleration, v sub t squared over r, and my given tangential acceleration, which is 4r, the alpha, the rotational acceleration times r. So when you square that, you get 16r squared. Square the 8, you get 64. Over here on the left, it's kind of fun because if you see how this is working out, v tangential, which is r times omega, that's a relationship that we have over here. So I'm plugging that in. I'm taking this r omega, I'm plugging it in for v sub t. All right? And what's going to happen there is when you all said and done in that big situation here, this term here, you're going to have basically r squared times omega to the 4th. R squared omega to the 4th. That's fun. How often do you get to do an omega to the 4th? That's pretty awesome. Plus 16r squared equals 64. And they give us omega as being at that particular point in time, at that instant, of 2 radians per second. So it's going to be 2 to the 4th. Wow, 2 to the 4th. Well, 2 to the 4th is 2 times 2 times 2 times 2. That's 16. Okay. So this is looking pretty good here. This is going to be 16r squared plus 16r squared equals 64. That means 32r squared equals 64. That means r squared equals 2. Or in other words, r equals the square root of 2, which is going to be 1.41 meters. Voila. Way to go.